There are two types of heat treatment. So one is referred as a bulk heat treatment, and one more is the surface heat treatment. So what we have discussed yesterday, that is annealing operation, normalizing operation, hardening operation, and tempering operation. All those things will come under bulk heat treatment process. The bulk heat treatment process means the total volume of the material is heat treated. That's why in the heat treatment step, first you are heating the material above austenizing temperature. Then next operation is soaking operation. Soaking is that nothing but you have to keep the component in a salt bath for a long period of time. That depending upon the thickness of the component, so that whole material is austenized. So austenized in the sense there is a different microstructure at room temperature, like the ferritic microstructure. It is transformed to austenitic microstructure above 727 degrees Celsius for the steel. That's why you have to soak it for almost half an hour or 30 minutes, depending upon the thickness of the sample. If the thickness of the sample is very small, in such cases, it may require few minutes. If the thickness is around 10 centimeter, then you may soak it for almost half an hour or 1 hour. Then whole volume of the material or your steel is reaching austenizing temperature, above austenizing temperature. Once it reaches, we can make sure that all the phases within the material is austenizing temperature. So that is nothing but your bulk heat treatment process. In bulk heat treatment process, so annealing is the one process, normalizing, the hardening and tempering. So in general, you can have to remember, if you cool the material very, very slowly, then you will get soft material. Then such process is referred as the annealing process. It is nothing but a furnace cooling. Then one more process is normalizing process. So where cooling is done slowly or medium cooling, that is nothing but air quenching or air cooling. It means your once material is heated above 727 degrees Celsius, after soaking for a few minutes or a few hours, you have to take out the component, you have to keep it in the open air or atmosphere or the floor, so that cooling rate is medium. Then such type of structure material process is referred as a normalizing process or air quenching process. So normalizing process, the ductility will be slightly decreased and toughness will be increased. But in some cases, we require complete harder material. That is a hardening heat treatment process. That is referred to the hardening heat treatment process. That is nothing but water quenching or oil quenching. What you have done the experiment in material testing laboratory. Then it is referred as the hardening process. The microstructure obtained in the hardening process is martensite. The martensite is the one more phase of the heat treatment. So martensite is one more heat treatment process. Or we can say that non-equilibrium phases of the iron carbon diagram. So where it is the hardest microstructure in the iron carbon diagram. It's a non-equilibrium microstructure. So non-equilibrium microstructure is nothing but, so this particular microstructure is not obtained at very, very small, very slow cooling. Very slow cooling. So such type of heat process is referred as a non-equilibrium microstructure. So non-equilibrium microstructures. So one is pyrite is an example for the non-equilibrium microstructure. Then you have studied about the binetic microstructure yesterday. That also comes under non-equilibrium microstructure. Then there is a one more is we have martensitic microstructure along with the austenite. There is a one more non-equilibrium microstructure. So anyhow, already you have discussed. So those everything will comes under the bulk heat treatment process. In general, you have to remember the whole volume of the material is heat treated, not only the surface. But there are some surface heat treatment process. So during the surface heat treatment process, only surface of the material is heated. You are not keeping the component in the keeping the component in the salt bath, or that is after soaking operation in the conventional heat treatment process. Instead of that, you are heating only the surface by the gas, this flame hardening, or it is after regular oxyacetylene flame. You are familiar by using the oxyacetylene flame, so we can heat the complete material. There is a one more heat treatment process that will go to next slide. So whatever may be the type of the heat treatment. So during our heat treatment, there are different treatment, but you are concentrating only on the thermal heat treatment. Just I am giving the conclusion. Already you have discussed about this slide. There's a thermal process. We can treat the material in different way. Either chemically we can treat, mechanically we can treat. So that is the mechanical treating is nothing but you are going for a small deformation. Because of that, you will get strain hardening. There is a one more process. The material will get hardened because of small elastic as well as plastic deformation. That is not now. It is required for as per your syllabus. But as per your syllabus, you are going for the thermal heat treatment. Normally, you are referring it as the heat treatment, and you are discussing only about the steel. Most of the topics you are covered with steel, not any other material. So if you see the broader classification of the steel, this heat treatment process, already we have discussed. So bulk heat treatment process, we have annealing, normalizing, hardening and tempering. Then we have malt tempering and ash tempering. The last yesterday you have discussed these two processes are left out. You have to discuss about this malt tempering and ash tempering. Then annealing with a very slow cooling process, normalizing very air quenching or medium cooling process. The hardening is a fast cooling process. But once the material gets hardened, so during hardening heat treatment, the material becomes too hard, then it cannot be used in the service. That's why you have to decrease the hardness by small amount. So then set type of heat treatment process is referred as the tempering process. Again, it is a secondary heat treatment process. The tempering is the secondary heat treatment process. After hardening treatment, the tempering treatment is done. The main purpose of tempering treatment is, so once the material undergone hardening treatment, the material is too hard, and whenever material is too hard, its strength will be comes down, and ductility will be comes down. Hardness increases to a very high level because of microstructure that is referred as martensitic phase or microstructure. To reduce the hardness which is obtained during hardening process, then we can be reduced by secondary heat treatment process. That is nothing but your tempering process. Then you have studied already the TTT diagram, temperature time transformation diagram. It is also referred as isothermal process. Isothermal process in the sense the complete heat treatment takes place, or treatment or phase change takes place at constant temperature. For that, we are getting some this phases like a binite phase or perlite phase, etc. But in even binite also, there is a small amount of this austenite. To get 100% austenite or 100% binite, you have to go for one more process. So it is a malt tempering process as well as ash tempering process. In general, you have to remember in ash tempering process, the microstructure obtained is 100% martensite. That you have to remember. Don't confuse. The malt tempering means you are getting the one more microstructure that is nothing but a bainite. Ash tempering process, the microstructure obtained is not martensite. It is 100% martensite. Some cooling process, then constant temperature, the transformation process. Then when you come to thermal process, as per your syllabus, you have to study two heat treatment process. One is flame hardening and one more is induction hardening that already we have discussed. In the flame hardening, material is heated. One is the surface of the material is heated and suddenly water is sprayed. So that means heating and cooling takes place. Heating takes place. How much time it is time taken for heating, that is not so important for heat treatment process. How much time it is taken for cooling process. We are concentrating more on cooling process, not heating process. So in the case of flame hardening, oxyacetylene flame is used for heating the material above austenizing temperature. Around that would be around 727 degrees Celsius. The most of the time you are heating around 800 degrees Celsius. Then there is an immediate water is sprayed on the water is sprayed on the surface. Because of that, the surface get hardening. Instead of using the flame, oxyacetylene flame, in our purpose is only to heat the surface. We can use electrical sources. The induction principle can be used. So this electrical wires you have to wound, then you have to supply the current. So when current is passed, because of the resistance in the material, that electrical conductor, electrical wire, so heat is generated. That heat is used for the induction hardening process. So now when you come to annealing process, one is recrystallization annealing, that is after recrystallization. The recrystallization is, crystal is nothing but a grain. So it is also the one is grain. One more name for the crystal is the grain as crystal. Both are almost same, no difference. So what is recrystallization? The new grains will be formed, or existing grain size is increases or decreases. The shape of the grain also changes. You have studied about the spheroidizing, spheroidizing heat treatment process. The final shape of the grain is almost like a spherical, the sphere. Because of that, we are getting good machining properties. Even in the cast iron, there is one more SG iron. In the final microstructure, we have one phase that is nothing but the spheroidal shaped phases will get, or we can in simple way. So carbon, it is in the form of carbon. It is finally it is in the form of spheroidal shape. Then because of the spherical shape, the machinability of the carbon cast iron is also increases. Even machinability of steel also increases. That means finally inside the material you are changing the crystal size, the crystal shape, or you are changing the phases, let it be from austenite to pearlite phase, or austenite to bainite phase, or austenite to the martensite phase. By changing these phases, we can change the properties. So that process is referred to the recrystallization process. The recrystallization process means new crystals are developed. Not all new crystals, only few new crystals are developed. And existing grains, the size may increase, shape may be increased. That is what is the recrystallization annealing. Then stress relief annealing. What is? Can you give one example for residual stresses? Heard about residual stresses? One example for residual stresses. One example, what is meant by residual, or give an example, that's sufficient. There are two types of stresses. In mechanics of material, you studied most of the cases, you studied only one type of stresses. So when material is loaded, then the stress is developed in the material. That stress is given by the load divided by cross section area. That is regular mechanical stress. The complete stress is developed because of the loading. Suppose you are carrying around, let it be around 50 kg of load, you are stressed and you are strained also. When you're carrying around 50 kg, so your body may slightly bend. That is nothing but strain. So that is a one type of stress. Suppose today morning you have some examination. So 9:30, you are not carrying any load, but still you are stressed. So before entering the examination, you are already stressed. That's the common meaning. Suppose question paper is very tough, still you are stressed further, but you are not carrying any load. Even if you carry the load, that is the, just I am giving example, what is the internal stresses or residual stresses. Even before going for the examination, you have some stress before seeing the question paper itself. That is stress is reside in your mind. So examination may be what type of question paper it comes, how much I can score, all those things will be stressed, but without carrying any load. That type of stresses are residual stress. When you come to mechanical engineering, imagine you have one component, so you are not applied any load on the component, still some amount of stress is existing in the component without any load. Then such type of stresses are referred as the residual stresses. Even if there is no thermal load also, still the amount of stresses will be there. But in as per mechanics of materials formulas, if there is no load, the stress is zero. The stress is given by force divided by area. But still, some amount of residual stress will be there. That may be produced during your metal forming process or forging process or drawing process or any other the manufacturing process. Even during machining process also, there may be some amount of stresses developed in the material. That is about the residual stresses. You have to relieve these stresses. To relieve these residual stresses, so we require some amount of treatment. So that is nothing but a stress relief annealing. Like what you are doing after finishing your exams, you may go to party or some good restaurant. So that is relief from examination tension. You are doing some party. In the similar way, when material is undergone huge amount of stresses, the residual stresses, you have to relieve that stress. That process can be that can be done by annealing heat treatment process. There is one more heat treatment process. So that is nothing but the spheroidization annealing. So finally, you are getting a grain. The grain will be almost in the spherical shape. When grain is almost in the spherical shape, so then such type of process is referred as a spheroidizing annealing process. Because of the spherical nature of the grain, it is almost like a SG iron. SG iron. So we are getting spheroidal or spherical grain or crystal. Because of that, you are getting good machinability. So this, if you remember that, but there are some plots and temperature range. When you ask for the annealing, you can write 1, 2, 3, 4. These are the type of annealing. For one, you give an explanation. Full annealing. The whole the volume of the material is undergone annealing in the case of full annealing. The recrystallization is also almost like a full annealing. The stress relief, suppose you have done the machining process. So only during the machining process, only surface of the material will undergo some amount of residual stresses. To relieve that, we can go for this type of annealing. It's again 1 minute. So this is the classification. Then we'll not go through this straight away. I'll finish this classification. So this is the one more. This diagram is available in Panish textbook or any textbooks. This is the classification. Here there's a mistake. Tempering is not a harsh tempering and mass tempering. Tempering is a totally different process. There may be mistake here itself, slide itself. So now I'm talking about the types of surface heat treatment already we have discussed. Just if you show some photos, there is a one test that is referred as a JOMINY END-QUENCH test. It is mainly to study how the hardness of the material changes within the surface itself, within the material itself. So now imagine this is the steel specimen. This steel specimen is heated above austenizing temperature. I am using the term austenizing temperature, or above lower critical temperature, or A1 line. A1 line or austenizing temperature if it is a eutectoid steel. Then you have to quench this material. Quenching is nothing but you have to put the water jet from the bottom. What you are putting the water jet. So once you put water jet, or if you sprinkle the water on this surface, then hardness will be changed. Where will you have the maximum hardness? At the bottom surface or top surface of the specimen?
Bottom surface.
From this point to this point, it is this. From this point to this point, this is the complete specimen. The top portion is the specimen holder, because water is quenched or water is sprayed on the surface. So whenever there is a water is sprayed on the surface, it is not sprayed on the surface. If from the external like an ordinary person, your water is specimen is heated, so water is sprayed. So that's all, nothing else. Then the specimen is cooled. Those are the inference the ordinary people may understand. They can get or they can understand. But being in mechanical engineering, it is not heating and cooling process. Other than heating and cooling process, so once you heat the material to the red hot condition or above lower critical temperature, I'm using the term lower critical temperature, or above 727 degrees Celsius, or there is one more line. What is the name of that line? 727 degrees Celsius. Is it A1?
Austenite temperature.
Huh?
Austenite temperature.
That is the austenizing temperature. That's also correct. That line is referred as, there are three lines are there. One is A1 line, one more is ACM line, and one more is A3 line. Above 727 degrees Celsius, you'll get on horizontal line in iron carbon diagram in your all heat treatment process. That line is referred as
Upper critical temperature.
Not upper critical temperature. That is referred as a lower critical temperature. A1 line is a lower critical temperature.
Yes.
You are referring that as A1 line. Most of the books, they are referred as heating the material above A1 line for eutectoid steel. If the composition of steel is eutectoid, then only you have to heat above 727 degrees Celsius. Then complete material is transferred from this perlite or austenite. Austenite is nothing but your alpha iron to the austenite. The complete phase. Imagine this is a heat specimen. You are heated above 727 degrees Celsius, subject to condition that this particular specimen is having eutectoid composition. If it is this specimen is at eutectoid composition, then the whole volume surface of the specimen will get heated. So the surface, the only surface of the specimen, there is a transformation from, let it be, the alpha iron to the austenite. There's a transformation. So inside the material, it's not like what ordinary people think. You have to think. So whenever material is heated above 727 degrees Celsius for eutectoid steel, where composition of the carbon is 0.76 or 0.8, then all the alpha iron or this ferrite is transformed to austenite. That's one part. Then we are concentrating only on the austenite. This that red.
So I guess somebody is asking to join.
That Timareddy. You should not enter the class late, because every class I have to admit you. Only that is admission is possible when you enter before the regular timings. If class starts at 8:30, you have to enter the class exactly 8:30 or before 8:30. Then only I can admit. once I switch over to PPT mode, that is behind the screen, we don't get, only sometimes we get small sound. So let it be now. The composition compound is this component is the having eutectoid composition of 0.8. So once you heat above, almost most of the cases the red dot condition are above upper this A1 line or eutectoid temperature. It is also referred to eutectoid temperature or austenizing temperature. Complete the ferrite or alpha iron is transformed to the austenite. So now material is already heated. So now it is in the austenate phase. Now you have to spray the water. So once you spray the water, so there is a sudden cooling process. It is a sudden cooling process. There are three phases of type of cooling process: fast cooling, the slow cooling, and medium cooling. So this comes under fast cooling process. So when you cool it very fastly by the spray of water, so your austenite is transformed to the molten site. You have seen yesterday CCC diagram as well as TTT diagram. I told you to practice those diagrams before coming to the class. So your complete austenite is transformed to molten site. Because of this transformation, the material get hardened. Then you are spraying the water from the bottom. You are spraying the water from the bottom. This portion, the hardness of the material is more because it is directly in contact with the this cooled very fastly, because jet of water is falls sprayed on this surface. But over a period of time, slowly the specimen is cooled from bottom end to the top end. So here the top end cooling rate is little bit slower. Bottom end the cooling rate is very faster, but top end the cooling is very slow. Because of very slow cooling, or it is referred to as slow air quenching. It is either slow air quenching. There may be loss of heat because of the conduction also, but let it be air quenching. The slow cooling. So hardness at the top portion of the specimen is less compared to the bottom specimen, because bottom specimen is subject to the very fast cooling. Top portion of the specimen is subject to slow cooling. So now if you draw this Rockwell hardness, let it be y-axis refers to the Rockwell hardness number. Let it be hardness number. So distance from the bottom, distance from the quenched end. So here, this is the distance from the quenched end. So exactly bottommost surface hardness is 60. So at a distance of 26, 26 into 1 by 6. That means if you go from the bottom, instead of referring this number, you can understand better. So you go from the bottom to top, the hardness is decreases. So because the top portion it is air quenched, bottom portion it is the water quenched or rapid cooling process. We can see here. So here in the top, if you go in this, if you cut this after this particular test, if you cut the material, this bottom most material, if you study the microstructure, you will get molten site. You can see here. It is not only this experiment. So you are getting the microstructure or phase. There is a phase transformation from austenite to molten site. Here we can say it is a molten site. But in between at the midpoint, there may be only 50% molten site. The remaining may be austenite itself or perlite. It may be almost of the time it is a perlite. But if we go from about this particular point, so here there is a microstructure is the perlite. Because of the perlite microstructure, the hardness is only 20. That means by going by heat treatment, we can change the hardness. Imagine you have purchased the steel from the market. It is available in the standard composition, and there is imagine the steel is having around hardness of 40. Hardness number is 40. So depending upon the heat treatment, we can increase the hardness number 40 to 80 by air quenching or oil quenching. Or if you go by furnace cooling, etc., by annealing process, we can decrease the hardness. That's the advantage of your heat treatment process. Without changing the composition, you are not changing the composition. By changing the composition also, we can change the hardness. By increasing the carbon content, we can increase the hardness. Even if you use sand mold, or if you use the metallic mode, there also we can change the hardness number. But once material is produced from the industry, like a Tata Steel, Jindal Steel, other steels companies, major steel companies, depending upon our requirement, we can change the properties. Either we can change the complete whole volume properties, that is nothing but your bulk heat treatment, or we can change the property only at the surface. That is a Gemini. This is a JOMINY END-QUENCH test. So now you can see here, all dimensions are fixed. Everything is information is available in the textbook. You can draw this diagram. This diagram, if you draw one curve, that is sufficient. Very close to the water jet, hardness is very high. HRC means hardness number. So that is the Rockwell testing, because you are used whenever you are referring hardness number. So you have to mention whether you use the Wicker hardness testing machine, or Brinell hardness testing machine, or Rockwell hardness testing machine, because the dimension is totally different, the procedure is different, loading applied is different in all three cases. So for the same specimen, if you found out hardness by Rockwell or Brinell as well as Wicker's, hardness number will differ. That's why whenever you are specifying the hardness number, so you have to specify which hardness test you are using. HR means Rockwell hardness. The BR means Brinell hardness testing. VR means Wicker hardness testing. There is a one process that is referred to as case hardening. So there is in most of the hardening process, one is transformation from austenite to the martenite. We can change the properties. So one more way we can go for the improve the hardness is you have to put more and more amount of carbon. We have low carbon steel, high carbon steel, and medium carbon steel. High carbon steel, the hardness is very, very high. Because of the presence of carbon, hardness may increase. Now we are talking about the surface heat treatment. Only surface of the material you have to heat treat. Only surface of the material you have to make it hard. So to make it hard, so then we cannot go for a hardening, regular hardening treatment, or normalizing treatment, or annealing treatment. If you go for those treatment, whole material will get hardened. To avoid that, you have to go for the surface hardening. One of the surface hardening method is case hardening. Here we know that when you put more and more percentage of carbon, the material get hardened. I am talking only about the steel. So only you have to put more and more atoms, so carbon, at the surface. Is it possible with the help of your casting process? Can you make the component only surfaces having more carbon? Imagine you are doing casting process. You have to produce one cylindrical component. So you have to put more and more amount of carbon only on the surface. No, it is not possible. There are a lot of technical challenges. So you are you imagine you have the Fe is there, steel is there, and the iron. You are adding carbon. You are mixing it. It is in the molten state. You cannot move only the carbon atom towards the outer surface of the specimen, or during the saltification, the carbon atom will rearrange themselves. We cannot force them to go and occupy only on the surface of the material. That is not possible. So naturally, the carbon is almost uniformly distributed in the material. So how to put more amount of carbon on the surface? We cannot paint with the carbon atoms on the surface. The carbon and Fe, you should form interstitial solid solution. Carbon and Fe are the interstitial solid solution. Example for the interstitial solid solution. So you have to put the carbon atom in FCC structure, because at the lower temperature it is at the FCC structure. So each carbon atom is having so each Fe is having in the BCC structure. Each carbon is having one Fe atom. Inside some amount of space is available. You have to push this carbon atom into interstitial spaces of BCC unit cell. That is our requirement when you come to the carburising process. We have Fe atom. So Fe, this Fe atom, Fe is in BCC structure at lower temperature. Yet you are already studied in the previous class. You have to put the carbon atom inside the lattice structure of BCC. That is, you cannot physically move the carbon atom, take the carbon atom from some material. You cannot inject into the BCC structure. But you have to diffuse. That process is referred to the diffusion process. You have to heat the material. So you have to keep the component inside the furnace. That is referred to, first one is referred to packed carburising. You can see here now, you understand what is the requirement. You have to diffuse carbon atom into the surface of the steel material. Surface of the steel material is nothing but you have to diffuse carbon atom into the BCC structure. We have the BCC. There's a small amount of spaces are available within the BCC structure. It is around 30% space is empty. In that space, you have to put the carbon atom. That process is referred to the diffusion process. The diffusion process will not take place at room temperature. For that, we require carbonaceous gases. From the CO2 gas, it will be dissolved when it is heated to the very high temperature. We get nascent carbon and oxygen, O2. That particular carbon atom should diffuse it into the component, the surface of the component. So then the percentage of carbon on the surface of the component is more compared to the core part of the component. Hence, only surface will get heat treated or hardened, or we can say that the surface of the specimen, let it be shaft. So only in the surface, the percentage of carbon is around 0.8%. That will be 0.8%. But inside core part, the percentage of carbon is around 0.4. Initially, the whole specimen is having 0.4% of carbon. After surface heat treatment, the inside part of the specimen, the percentage of carbon remains same, that is 0.4%. Only surface part of the component, the hardness is not hardness. In later stage, we discuss the hardness. The percentage of carbon increases from 0.4% to 0.8 by diffusing carbon atom from the carbonaceous gases at very high temperature. That again, it is below this above austenizing temperature. Same process here. So depending upon the physical structures we are using, we can classify into different types of surface heat treatment. Both basic concept is same. Just you have to diffuse carbon atom into the surface of the steel. So if you keep the component in the packed the component inside the furnace, this is a closed chamber. You have to heat it. You have to heat the complete closed chamber. Only atoms will diffuse. Already studied about the diffusion process. Atoms will diffuse only at higher temperature, not at lower temperature. Don't think that if you keep the steel on the in open air, imagine steels are available. It is most of the construction steels everywhere we have the steel. Don't think that carbon atoms will go and occupy in the interstitial spaces of the BCC structure. That will not happen because at lower temperature, the diffusion process is not happening in the case of metal. But at room temperature, the liquid state diffusion process may take place. If you drop one drop of ink into the water, the diffusion takes place. The ink will spreads into the water. That is in the case of liquid state diffusion process. But you are talking about a solid state diffusion process. Solid state diffusion process to take place, you require higher temperature. That's why all components are packed, and this packing or this packed component or bins are kept inside the furnace, and these packed components are surrounded by coal, etc., so that it will generate some carbonaceous gases like a CO or CO2. Then, if over a period of time, CO will be dissolved into C and O2, or CO2 will be dissolved into C and O2, and finally, this carbon is diffused into the nascent carbon is diffused into the surface of the component. But the carbon is not, isolated carbon atoms are not available in the even any gases. It is either in the CO, normally it is in the form of COX, we can say. X may be 1 or X may be 2. There is one more liquid carburizing process. So again, there are some process. Finally, nascent carbon will be produced. It is in the liquid state. Your medium carbonous medium is liquid state. Don't think that metal is in the liquid state. Gas carburizing. So again, what you discussed, one is carbon gas. Nitriding process, again, if you diffuse the nitrogen atom into the surface, the other theory part we can read. Everything is very simple as per this surface heat treatment is considered. In heat treatment process, it's very simple. In general, you have to remember, in the case of nitriding surface heat treatment, the nitrogen atoms or N atoms are diffused into the surface. So again, to get nascent or isolated N atoms, then there are some chemical reaction. Those reactions and component you have to the reactant you have to remember. In the case of nitriding operation, the nitrogen atoms are diffused into the steel surface. In the case of carburizing heat treatment, the carbon atoms are diffused into the surface of the steel. Then it is referred to carburizing, or it may be nitriding operation. Again, everywhere it is heating is required. The heating is normally below 727 degrees. We have ammonia, NH4. I think it is NH4. That will be dissolved into and finally get N atoms or nascent ammonia. So ammonia is. So again, you have to keep imagine time required for case depth. Imagine suppose we want to diffuse the nitrogen atom from 0.5 to around 0.1 mm. So how much time is required? It is almost around 10 hours is required. Diffuse nitrogen atom into the surface of the specimen of having depth of 0.5 to 0.7 mm, around 10 hours is required. Suppose you want to make the harder, more depth, let it be around 1 mm depth, up to 1 mm depth, you have to make the surface harder. Then you may require around 20 hours or more than 20 hours. So nitriding develops very high hardness. It may be around 70. So no machining is required. The cyaniding process. So again, in the case of cyaniding process, the cyanides. So again, it is a heat treatment process. So finally, cyanide atoms are diffused into the surfaces. Then it is a cyaniding process. So most of the cases in the cyaniding process, both nitrogen atoms as well as carbon atoms produced during the cyaniding process. Where the chemical reaction or small chemical reactions are available in the textbook, you can refer. Those are simple reaction. So finally, we have nitrogen atom and carbon atom. Those both will be diffused into the surface of the steel. Don't think that one is CN or cyanide. Both nitrogen as well as carbon atoms are diffused into the surface of the steel. Then it is referred as the cyaniding heat treatment process. This is flame hardening process. Already we have discussed. So we have this is the arrangement. Imagine this is a specimen. We have carriage. You are moving the carriage. In the front there is a flame. The flame is followed by once if you move the carriage forward, because of the flame surfaces get heated, it is followed by cold water spraying. It is followed by the cold water spraying. So Hari Anandan. So you have to join the class in time. Otherwise, it is very difficult to admit you. It's very simple. We have to heat the material above oscillating temperature. So again, once you understand the heat treatment concept, I already spent around 3 to 4 hours for explain the basic heat treatment concept. It is a physical arrangement for heat treatment. This is a physical arrangement. There is an oxyacetylene flame, burner flame. Using this, you are heating the material above austenizing temperature or A1 line or 727 degrees Celsius. Then it is suddenly cooled by spray of water. Because of the sudden cooling, the complete austenite is transformed to the molten site. Molten site is the hardest the microstructure in the steel. So because of that, the surface is hardened. So depending upon the speed of the carriage or velocity of the carriage, so depth of the hardening will be decided. If you move the carriage fastly, only surface depth of 0.1 may be hardened, 0.1 mm. If you move it very slowly, then more time is available. So the specimen is heated to the more depth, and we may get hardness up to 0.1 mm or up to 1 mm. So everything can be controlled, but it is a schematic diagram. Again, carriage is moved by even robotic arrangement, some other automated. Its whole system is automated. It's not as simple as this diagram. This diagram is only for the exemption point. You can refer. We can use progressive flame hardening, spinning. There are different types of flame hardening. There is induction hardening. A high frequency current is passed through the specimen by induction coil. Because of that induction process, the heat is generated only on the surface. But only one advantage of induction hardening is we have control over the heating process. Because we can control, once you are able to control the current flowing into the specimen, this on the surface, so we can control the heating. That is the one advantage. For the small component, especially cylindrical component, the induction hardening is used. Then it will be followed by cooling process. So now we can see there is a water spray. Because of water spray, so it is cooled, hence it will get hardened. That is referred as induction hardening. Then one more process is referred to the edge hardening. So edge hardening is, what is meant by edge? Why you are saying using the term edge? It is happening only in the aluminum copper alloy. So this is development or the research is not intentional. It is unintentional. So it is happening aluminum copper alloy for 4% copper, not for all percentage of copper. So again we have, but again you tell me. Okay. So it is not happening in the case of steel. That is comes under heat treatment of the non-ferrous material, especially aluminum copper alloy. This edge hardening is more effective only for aluminum copper alloy. The percentage of copper is the percentage of the copper is 4%. So then only it is happening. So suppose one scientist, I think I've forgotten his name also, he conducted the experiment. Like you're coming to the lab, you conducted the experiment. Imagine it is a heat treatment process. Imagine you have heat treated around 10 specimen. Then on the same day, you have tested hardness of the material for only 5 specimen. Imagine it's almost 4:30. Then you are within 4:30, you are able to test around 5 specimen out of 10 specimen, and it get hardness number. That it be hardness number is around 50. The 50 hardness number for the first 5 setup. All composition same, treatment everything is same. So because of the lack of time, because of hurry, we are able to finish only 5 specimen. You have noted the hardness number. That it be hardness number is 50. And next week you are coming on the same day, same time after 1 week. The remaining 5 samples he tested, and after testing, so he expected and he got some unexpected result. Instead of hardness is 50, just I'm giving example to understand the concept. I'm not giving the exact numbers, etc. So instead of getting hardness number 50, because all specimens having same composition, process followed same, instead of that, he got hardness number of around 70 for remaining 5 specimen. So what might be the reason? Imagine assuming that everything is correct, all procedure followed is correct, all hardness testing machines are correct. What might be the procedure? This reason. So age is referred to with respect to time. So 1 year is again time. Our age, my age is say around 40. Is again with respect to time. 40 into 360 into all those things we can calculate in terms of seconds or minutes or hours. So age is referred to that time. So after 1 week time, there is a transformation. Initially we have alpha phase. So alpha phase is transformed. Alpha phase is transformed to alpha plus CuAl2 phase here. If you're going for very slow cooling process, we'll get one more phase. So alpha plus CuAl2. If you're going for immediately quenching process, we'll get only alpha. Even quenching also, we'll get alpha phase only. There may be small change in hardness. Then if it is age hardening, so then we'll get alpha plus CuLu2. That means here also we have alpha plus CuL2. This is a phase. This you can see. These are two diagrams. This is also alpha plus CuL2. This is also you have alpha plus CuL2. I have given an example of Lakshman. So there are two Lakshmans. Those two Lakshmans are not resembling each other. One is maybe very tall, one more is very strong. But here also it is alpha plus CuL2. Here also alpha plus CuAl2. The here phase is different, or we can say that Lakshman 1 phase is different from Lakshman 2 phase. This is let it be alpha plus CuAl2 is Lakshman 1. Alpha plus CuAl2 is Lakshman 2. So their phases are different. You can see here. Here we have the totally different phase. The grains are totally different. And here grains are totally different. If you're going for the very, very slow cooling, we'll get this particular grain structure. Because of this very, very slow cooling, that is nothing but age hardening. So suddenly hardness is increased. Such type of hardening process is referred as the age hardening process. It is happening only for the aluminum copper alloy of 4%. It is not within that, by conducting only remain 10 specimen is not concluded. He has not come out with his research finding. Then because of the curiosity, he conducted many tests. He kept it for 1 week or 2 weeks or 3 weeks at room temperature. Then again, after conducting so many tests for over a period of few months or few years, so finally he concluded, if you're going for very, very slow cooling, that process is referred as the age hardening process. So we will get totally new microstructure. So this new microstructure is this microstructure. Even though we have alpha plus CuAl2 here as well as if you go for a regular heat treatment process, this bottom process is completed within few minutes. Quenching, then aging, so a few minutes. But here it takes place around after 1 week or 2 weeks or 3 weeks. So there we are getting the different microstructure. Because of that, the hardness change of transformation from alpha phase to different phase takes place over a period of time, 1 week or 2 weeks or 3 weeks. That everything is depending on the temperature at which you are keeping. Because of that, it is referred as the age hardening process. That for age hardening process, you have to draw this phase diagram. Y-axis in the phase diagram temperature, x-axis it is the composition. So you can see here under aging, optimum aging, and over aging. This depending upon how many hours are required. We can classify into the age hardening into under aging. Under aging means it takes place, hardening takes place with minimum time. The optimum aging, over aging, everything is for the given specimen. Everything is depending upon the composition or at what temperature, depending upon the cooling rate also. There is one more precipitation hardening we'll discuss later. I think another 1 hour is required to complete your heat treatment process. That we will finish the next class. Well, study day to day. Don't waste your time. Otherwise, understanding heat treatment phase diagram, iron carbon diagram is a little bit difficulties. You may have some difficulties. I think you are able to put your USC number. Those who are not entered your USC number, please enter. I'll take the attendance from your chat box. I don't call your attendance. And those who have joined recently, especially if you have first hour, come in time or before time. So then you can join. Otherwise, in between, if you request for admitting, it is happening in the background screen, not in the main PPT. Then it is very difficult to admit you. Okay, if you don't have any doubts, I stop my class. So don't waste your time, especially for don't keep these topics before 1 week before the examination. These things cannot be studied with short time. It requires its own time. That's why study this topic day to day and try to understand, practice these diagrams It is available in Panish textbook or any other textbook you are referring.